In this video, I'm demonstrating example microgrid controller off-grid. You go to the File, Launchpad, Tutorial Examples, Renewables, Example microgrid controller off-grid. We launch, open the project. In this microgrid, we have a large solar PV, we have two battery energy storage, we have a fuel cell and conventional generation as a backup, and we have load. And as you see, this is an off-grid microgrid and there is no grid connection. In this system, we have ETAP microgrid controller that is responsible for active power control, reactive power control, frequency control, black start. Let's start with looking at the available scenarios in this project. The first scenario that we would like to take a look is the rule base. So let's run this scenario. In rule-based scenario, the microgrid controller is set to minimize the emission. So basically, in this case, the microgrid controller tries to maximize the renewable generation. If there is an excess of renewable generation, it will be charging the batteries. And whenever there is a lack of generation, the battery is going to start discharge and providing enough power to supply the load. If there's not enough energy stored in the battery, the microgrid controller is command the fuel cell first and then the diesel generator or conventional generator to supply the loads. Now let's look at the results of the system. Let's plot rule base, AC cables, and all the generations and the loads and battery. So in this case, as you see, as the sun rises, the solar generation goes up, and if the solar generation is more than the load, is gonna charge the battery, and as the sun sets and the load becomes greater than the generations, the batteries, they start discharging. And in this case, which is a case for a 100% renewable microgrid, you see that the fuel cell and the generator are not used for the normal operation. Now let's go ahead and run the same case when it's a cloudy day. So we're going to have a cloudy day. That is, you see here that in the events are defined, we're going to have a cloudy 90% cloud in the system, and we're going to run this case and see that how the microgrid controller is going to utilize the fuel cell and generator to supply the loads. Now let's look at the results of this case. So I'm plotting the rule base under cloud and all the cables, and let's look at the performance of the system in this case. As you see, at 12 o'clock, we have the 90% cloud. So the generation drops. And in this case, what will happen is that the battery is gonna go ahead to discharge the power to the system to supply the load. And at the point that the battery energy depletes or reaches to its SOC mean, the microgrid controller is gonna command the generator and fuel cell to start generating and to supplying the load. And as you see in this case, both the fuel cell and generator are used. Let's also look at the battery state of charge. So I'm gonna go look at the battery state of charge. And as you see, during the sunrise, the batteries are starting charging, and at 12 o'clock when there was a cloud, the batteries start discharging, and at around about 6:30, the battery reaches its SOC mean, which is 10%, and the microgrid controller commands the fuel cell and generator to supply the load. ETAP microgrid controller not only provides the rule-based algorithm for active power, but it also provides the optimal dispatch that minimizes the cost of operation. So in this case, you see that the method, rather than being mean emission, is selected as optimal dispatch. So if we run this case in the normal condition, so optimal dispatch, if I run, so in this scenario, it's going to use the load and generation forecast for the next 24 hours. It's going to run the optimal dispatch, which is the mixed integer linear program, and it's going to determine the optimal set point for various assets of the system. This case does not have any cloud. In a normal day when there is no cloud, so if we go and compare the results of the rule-based dispatch and optimal dispatch, you're going to see that the results are going to be more or less the same. And the reason for that is the optimal way to operate the system is to charge the battery whenever there is a chance and there's an excess of renewables, and discharge the battery when there is a lack of renewable generation. So in this case, you see that the optimal dispatch and the rule-based results are kind of matching. Keep in mind the optimal dispatch runs every 15 minutes, while rule-based can run faster every 5 seconds. So you see more granular results for the rule-based versus the optimal dispatch. Now let's go ahead and run a case of the optimal dispatch on a cloudy day. In this case, let's go ahead and plot. So we are looking at the optimal dispatch cloud and rule-based cloud, and we are looking at the cables for generator, battery. Let's just plot one of the batteries. Both batteries behave more or less the same, fuel cell, and let's see the performance comparison. So as you see, there are two different performance here after it becomes cloudy. In case of a rule base, as you remember, if I just uncheck the optimal dispatch, we are going to use the fuel cell when the battery depletes, and then we complement that with the generator. But in case of the optimal dispatch, because optimization knows the forecast and future of the system, knowing that there would be no solar at the end of the day, what's going to do is going to use the battery less and is going to use the fuel cell more. And this way is going to avoid using the synchronous generator in the long run. The next scenario that I would like to demonstrate is the secondary frequency control. In secondary frequency control, what we are doing is that in a typically a large renewable microgrids where they have multiple battery energy storage and the large solar, all assets, all the inverters contribute to the frequency control. So in this case, not a single device control the frequency. So if we go here to any of these battery controllers and look at the frequency control or active power control, if I go to the P control, you see that most of them, or for this case, they all have droop. This means that if there is a load increase in this system, the frequency is not going to come back to the nominal frequency. So in this case, the microgrid controller will be responsible to provide a secondary frequency control and bring the frequency back to the nominal frequency. So it has a PI controller to do that. This is a very new application in the microgrid with multiple inverters and large solar. So let's go ahead and run this case. So as you see here, we have events to increase the load. So we are increasing the load. Now, if I go and plot the frequency of the system in this case, voltage and frequency, let's just plot the frequency in this case. As you see, when there's an event, when there's a load increase, the frequency drops, and then the assets, the solar, the battery starts reacting immediately to bring up the frequency, but at the end, it would be the job of the microgrid controller to bring the frequency close to the nominal frequency. Now let's plot also the battery as well. As you see, when the frequency drops, the battery's primary controller immediately responds to bring back the frequency. However, because the frequency still is below the nominal frequency, the microgrid controller is going to slowly increase the generations of the battery to bring back the frequency to the 60 Hertz or to the nominal frequency. The next scenario that I would like to demonstrate is the voltage control. Now, let's look at this case. In green off-grid microgrid, not a single asset is responsible for voltage control. So all assets, they have the QV control for the voltage control. If I go to this battery control, the Q control, you see that the Q control has a droop. Means that this battery contributes to the voltage control the same as the PV and the other assets that's running in this system. When there's an event happens or there's a load change or there's a disturbance, the voltage at the point of measurement will not come to the set point that is set. So in this case, the microgrid controller reactive power control, which is kind of a secondary reactive power control, will be responsible to provide a Q control for this system. So if I run this case, in the study case, you see that we we have the reference voltage. So I'm trying to move from 100% to 105 to 101 and 101.5 at different times as per a steady case command. So I'm commanding the microgrid controller to adjust the voltage at a point of measurement. A microgrid controller is going to dispatch the assets to bring up the voltage at the point of interconnections. Keep in mind, some of the assets like the batteries and PVs, they have QV control and they compensate reactive power based on their point of common coupling, in this case these buses. But at the end, the microgrid controller keep increasing their set points to bring up the voltage at the point of measurement. So in this case, as you see, at 20 seconds, 60 seconds, and 100 seconds, we are sending a new command to microgrid controller. Now let's go ahead and plot the response of the system and look at the voltage. As you see, at the 20 seconds, we are trying to increase the voltage and bring it to the 100.5. At the 60 seconds, we send a command to bring it to 100.1. At 100 seconds, we increase the voltage to go to 100.01. So it takes several seconds because this is a secondary voltage control to bring the voltage to 101.5. The last scenario that I would like to demonstrate is the black start. So in this scenario, at 7 seconds, we're going to trip the circuit breakers of the battery and PV, and we're gonna force the system to go black. And then the microgrid controller is gonna start and black start the system and do the soft energizations of the battery energy storages and bring up the loads and solar generations and energize the system completely and restore all the loads. Okay, let's look at this case. At time 7 seconds, we trip all the assets and force the system to go to black. At 10 seconds, microgrid controller first trips all the loads, make sure the system is fully de-energized. The next step is that it's gonna soft energize or start the batteries. And as you see, voltage is about 5%. And as the time goes by, the microgrid controller does the soft energizations and increase the voltage of the batteries. And then it's gonna go ahead and bring up the loads one at a time. As you see here, loads coming one at a time. And then the renewables, the solar connects and ramps up slowly, and the microgrid fully becomes energized. Let's go ahead and plot the bus voltage first and see how the soft energization has happened. As you see, microgrid collapsed at 7 seconds. Microgrid controller did the soft energizations and tried to maintain the voltage by slowly energizing the load and generation to the system. Let's go ahead and plot the battery energy storage as well. As you see, as the load's increasing, the battery discharge level increases. And during all this time, microgrid also does secondary frequency control. And then once the solar gets connected, it's going to ramp up the solar slowly to make sure that the system remains stable. And as the solar generation goes up, the battery starts reducing its discharge level and goes actually at the end to the charging mode. If you're interested to learn more about ETAP microgrid solution, please visit our website etap.com and you will learn about ETAP microgrid controller solution, benefits, features, and there are lots of recordings and webinars available that you can learn more. Thank you.